Hey guys, welcome to Great Learning. Inferential statistics is such an important part of today's world of statistics, right? When you think about it, I can promise you one thing. You have actually made use of inferential statistics to a good amount of degree. In today's world, in fact, to give you in a little picture about what inferential statistics is doing, it plays a very key role in helping us analyze various things. Now, wherever you think you have a lot of metric, you have a lot of numerical data that you can track, assess, and analyze. Guess what? Inferential statistics, you can get way more insights, understand patterns, and do a lot of things which you thought was not possible. By making use of inferential statistics. There, any domain that you can think of, right? Be it healthcare, be it sales, be it logistics, be it marketing, be it anything. In today's world, of course, everything usually gets backed by machine learning or something related to artificial intelligence, and the insights that we usually derive out of these inferential statistics results, right? They do have to play a key role in many cases to actually take part in the training of a machine learning algorithm, or even to a fact where it has such a huge say on the end result that the overall project will basically become an inferential statistics project, right? So it is a huge world. It is very important, and I understand that all of you all are here to get a complete understanding of what inferential statistics is, and in this course we are going to do exactly that, right? So guys, welcome to this course by Great Learning. My name is Anirudh Rao. Let's get started, right? If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleague, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments. Coming to the first discussion, I think we definitely have to take a look at the agenda, right? So on this course, Inferential Statistics, what we are going to do is we're going to start this out by understanding and, taking a step back and finding the easiest way of how we can navigate across inferential statistics, right? So to do that, we're going to start this out by taking an introduction to statistics, understanding what statistics is, why we require it is very important. Because once you have a clarity about what statistics exactly is, you'll be wondering about, okay, so now I know what it does. Are there any types of various statistical analysis that you can go on to perform? Of course, there's various types of statistical analysis. We're going to take a look at all of them. I'm going to be giving you extremely simple examples so that not only you understand the concept, but later down the line, when you have to recall something, you can use the example to actually bring up the concept and remind yourself of the entire thing, right? So after, we go about understanding the various types of statistical analysis that's out there, we are going to take a deep dive into inferential statistics. We will get to understand what inferential statistics, how it works, why it works the way it does, and of course a lot more, as you can see. Now, another important thing about inferential statistics, to be very honest with all of you all, is that it's a really huge domain, right? It's a very vast domain wherein, when you say statistics, I can bet that you can have a textbook which probably has thousands of pages to cover the entire domain of it, because it's really big, and inferential statistics aims to sort of, simplify the complexity of what the world of statistics is. So, to understand inferential statistics completely, these are the concepts that govern the domain, right? We have things such as probability. We're going to be understanding what probability is, take one or two examples, understand something called conditional probability. Now, conditional probability has a very important say in inferential statistics. In fact, it has a huge say even in the world of, think about Bayes' theorem. You can think about naive Bayes algorithm in machine learning, right? So literally it's one thing that adds on to something else. And at the end of the day, the end result is maybe a very well-tuned machine learning algorithm. But to get to that algorithm, you require all of these statistical concepts to go there, right? That is what we're going to be concentrating on, knowing that it is possible. So we're going to be taking a look at conditional probability. We're going to be taking a look at two very, very important foundational concepts. We're going to have an introduction to understanding what the central limit theorem is. Don't worry, I am not going to bore you guys with telling you how we can go about to prove a theorem or anything as such. We are concerned about how we can understand what the concept is and how best we can use it. So we're going to take a look at that. And lastly, as you can see, hypothesis testing. I guarantee you, if you have clicked on this video, you might have heard of the term hypothesis testing, right? It's a really, really important thing, especially in the domain of statistics. So we are going to have to take a look at that. So guys, with this, I hope the agenda of what we are going to be covering in this course is clear to all of you all. With that, we can go on to begin with the first item on the agenda, which is introduction to statistics. Now, just before we actually go on to head towards the inferential statistics bit and to understand statistics, I just wanted to tell you guys the importance of statistics, right? We spoke about machine learning, we spoke about healthcare, we spoke about so many different domains, but I think the most trending domain that we have in today's world, as you might already know it, is data science. So every single time, I have a webinar, I have a lecture, anything on statistics, everyone just goes on to say, how can we use this for data science, right? One thing you have to understand is that for a data scientist's role, you require a lot of statistics and mathematics, right? Because the concept of mathematics will go on to be applied through statistics. And once you start applying statistics, that is when you get beautiful machine learning models, ways to handle large amount of data, ways to group the data. There's a lot of things you can do, right from bringing in data, analyzing it, applying machine learning models over it, getting your results, creating graphs out of it. Everywhere there, one step of the way, in one or the other tiny bit, you have a bit of statistics, right? So mainly we use statistics to gain some sort of insight from the data, to see what the data can tell us something new. And of course, as I just told you, right, it becomes very important that you understand the foundation of statistics, especially if you are also heading towards the domain of data science. I know that some of you all might not be looking towards data science, but it's very important for you to understand that even such a big domain such as data science actually has a backing, a stronging, a foundation, a pillar such as statistics. And eventually these tiny things are what makes the domain of data science as big and as beautiful as it is, right? So now we know a bit about the importance of statistics as well. So I think it's high time we dive right into understanding what statistics is. Now, ladies and gentlemen, to give you a little bit of picture about statistics, I think one really important thing that you're supposed to understand about statistics is how we can go on to attach a numerical metric to something that we can go on to later track, right? I'll give you an example. Think about the fact, think about, your scale, for example, the scale that we used to measure in schools and colleges and all of that. You'll realize that each of these scales that we use has a very structured numeric way through which we add more meaning to something, right? You just draw a line on a paper, it's a line. But with the help of a scale, you can say that, hey, this line is now 5 centimeters in length. If you have a protractor or something like that, you can use these tools to add more meaning to something which at the end of the day would have not gotten its meaning initially to get started with, right? That is exactly what's happening in statistics as well. It's not a standalone concept, but it is something that adds on to how you apply mathematics, and eventually once you use that, again, applied statistics goes on to the whole train of machine learning and whatnot, as we already saw. So statistics is nothing but a study of mathematics, and eventually a way of how we can go on to apply certain mathematical concepts, especially on the lines of pattern matching, on the lines of gaining insights from the data, on the lines of actually understanding more about the data, right? So that would be the textbook definition of what statistics is. Now, to understand statistics, right, it's a very wide term, and sometimes the meaning, sometimes, the way we go about telling it can become very vague, because it's a really huge thing that we're trying to cover in a small amount of time here, right? So what we are going to do is we're going to take a slightly different approach. I'm going to help you understand complete, to give you a complete clarity about statistics by making use of telling you what sort of data we bring into statistics, right? Because if I just say, hey, statistics is used for this, that, and something else, it will not add any meaning for you. But if I tell you, here are the various types of data, here is how we use them, and here is how we can apply the concepts of statistics over them, do you think that would be a better way for you guys to completely understand the domain? I know you're saying yes. So we are going to dive right into understanding some of the various types of data that we have actually seen in today's world, right? Well, to give you a little bit of picture, today we have a lot, right? We have a ton of variety of data. Now, by the time you actually heard the snap of my finger, we would have generated terabytes and terabytes worth of data. I promise you, by the time you heard that sound, we have generated enough data around the world that can fill all of your hard drives up, and then some, and then some. That's how much data we're generating every second in today's world, right? So of course, to simplify how we go on to attack the concept of data itself, data is generally divided into two types. We have categorical data and we have numerical data. Now, if you're keenly observing your screen, you can basically look at the images there, which basically describe what the types of data are, and you can take a quick guess about what it means, right? Numerical, what are we talking about numerical? Numerical basically talks about data which has numbers associated with them. Categorical data talks about how you can probably work with the data in a structured and a seamless manner, right? So what is numerical data is very easy to understand, but what are we trying to understand here, especially with the help of categorical data, right? Now, data is of two types. Just think about this. One side you have textual data, right? Text. Now whatever I am talking is textual data. Now we have numbers on the other side. For example, a mobile phone, something like that, right? It's completely numeric. Now what happens in the case of categorical data is categorical data helps us to assess and analyze mostly these textual data that we're talking about. As you can see, while handling textual data also, there can be a lot of types of it. There can be a good amount of variety to it, right? So we have three types of data here: ordered data, nominal data, and binary data. So what is ordered data? Whenever you say data is ordered, we're basically telling that, hey, you can approach the data and you have meaning not only to the data, but the way the data is put into place, right? Think about priority. I am very, very sure if you guys are college students or if you are in your job right now, your manager or your lecturer or someone is going to come to you and say, hey, these are the tasks that need to be done on priority, P0, P1, P2, right? You're giving an order to your data. And whenever there is any ranking, right? Think about a Formula 1 race. Think about any race or any event or even the Olympics. There's certain ranking, right? The person who pushes the most performance gets to stand on the top step of the podium, gets a gold medal. The second place gets a silver medal, third place gets a bronze medal. So many things, you know that. But we have an order there, 1, 2, 3, right? Especially in a Formula 1 race, you get the order for all the 20 drivers, like who finishes where. So there is order, even though it's numerical data that we're talking about to a certain degree, the order when you attach it to it, right? That's when we think about how we can go on to work with categorical data. And then we have nominal data. Nominal data is just textual data where there can be no set specific order through which you can track or assess or measure something, right? Now, whatever I am talking right now, you can consider it to be unordered data, because that is how any machine learning algorithm or anything that you would work with further with what I'm saying will actually look at it that way, and that's how it would process it as well, right? So whenever you have a conversation with your friends, whenever you're texting, whenever you're doing anything, where you're not using a lot of numbers or anything, you can call it unordered data for sure. Next, we have binary data. Now, binary data talks about true binary events, right? Ladies and gentlemen, binary, the concept of binary should be very familiar with us. In fact, the computer that I'm working on, the computer that you are seeing this on, your mobile phone, probably your watch, almost anything digital, in fact everything digital in today's world exists between these two states, 0 or 1. So it's actually binary. Whenever I ask you a question and say, hey guys, is this true or false, you have only two choices: binary, true, false, yes, no, 0, 1. Correct? Just think about it. So whenever you have any sort of data that replicates that, whenever I ask you a question and your answer is either yes or no, true or false, anything between only two options, that makes it binary, right? So that kind of an answer that you would give to any questions I ask, that you can easily consider that as binary data. But one thing you must understand with respect to numerical data is its main difference from categorical data is numerical data is measurable. Think about that scale example that I gave you, right? You can measure things. In fact, there's two types of numerical data in today's world. It's discrete data and it's continuous data.
Think about discrete data first. Discrete data talks about calendar days, right? So it is a specific order. It's going to arrive in the same ordered place, but at the end of the day, you know that each has its own division, right? So every month we have calendars date from 1 to 30 or 1 to 31 or something, and we don't go to 32. We reset back to 1 and we start all over again, right? So it's discrete. It's not continuous to a certain extent, and we keep repeating that entity, and we can measure each of those slots. Now, if I have to probably measure what I did on last Wednesday, I can do it. If I have to measure what I did maybe on the 20th of certain month, I can do it, right? That's important. And then you have continuous data. Continuous data is very simple. If you have certain order, not order, you have a certain way of actually predicting what might happen next, or a way of tracking in a structured manner what has happened in the past, that will basically give you a clue into continuous data, right? Because your data will vary in a very smooth, very structured increment or decrement for that matter. Think about the height of a person, right? Height of a person is a great example for continuous data. You usually start as an infant, you're very tiny, and you start growing, maybe to the age of 24, 25, you become 6 feet tall, and probably that's about it. Your height might plateau out for the rest of your life, and eventually there'll be very slight changes, ups and downs, and maybe when you're getting old, your height might reduce a little, right? So it's very continuous, and it's not like you're going to grow 10 feet today and lose 3 feet tomorrow. That just doesn't happen in the world of human beings, right? So that's a very good example. Think about age. Age is a fantastic example. So when the earth goes around the sun once, your age just goes up by 1. It doesn't go up by 2. I cannot choose to be 27 because I am 25 right now. When you think about it, I cannot say, hey, my birthday is very close by. I don't want 26. 26 seems boring. I want to become 27. Does that work? Maybe in a fantasy world, yes, but in the actual tracking world of how we talk about birthdays, how we talk about calendars, how we track age, you have this in a continuous fashion, right? 1, 2, 3, 4, 5, all the way to 100, and if you're lucky, way more than that. So that is a very good way for you guys to understand what sort of data we use to perform what sort of assessment that we're talking about, right? So I hope all of you all are clear with this. Now, coming on to understanding the next really important bit of statistics for you guys is for the fact that you might be asking, hey, so now we know that we generate a lot of data. Now we know we handle a variety of data for statistics, but how do we even collect data for statistics, right? It's very easy to say, hey, you go online and you collect a lot of data. You go to competitors, you collect a lot of data. Maybe you store all the data in your database. It's very easy to say, but for you as a learner, you need a very good amount of clarity on this. So let me explain how we can go about performing data collection for statistics. Right? It's a very interesting concept, and you'll absolutely love this. When we say population, right? What's the population of the earth? Couple of billions right now, right? So when you say population in the entire world, you generally take into aspect everything there is. Now, if I say, hey guys, here is my garden or something, and here is all the population of flowers. When I say population of flowers in my garden, it means every single flower in my entire garden. But what if I don't want to pluck every single flower out there? So instead of just taking in all the data in today's world, maybe I just want to take a little to start analyzing and to break data down into its simpler terms, correct? Now in that case, what I'll do is I'm going to pick up 3 flowers from my entire garden of flowers. What am I doing now? I am picking one small thing which is part of a larger thing, right? So in fact, even you can consider yourself to be a sample set. That's exactly what a sample set is. Now, I am a sample set in a world of population because I am one among multiple humans out there. You are one among multiple humans out there. Earth is one planet among multiple planets. So when you say population, basically in our term, whenever we are performing any experiment, whenever we are assessing something, if you're considering all the attributes and variables in discussion that makes it the population. If you just consider a part of it, it makes it the sample set. Now, what's interesting is, in many cases, why we actually go about doing this concept is very interesting. I told you we generate a ton of data, right? It's not in all of these cases where you just bring in heaps and heaps of data to perform analysis. You take one chunk out of that data, perform some analysis on that. That will give you a clue to probably about 70-80% of what your entire data is doing. Isn't that extremely efficient? Think about it for a second, because that's exactly what we do. And that's exactly why we even go about saying it's very easy for you to say, hey, I'm going to go pluck every single flower in your garden, not a big deal. Correct. Now, if I say, hey, probably I want to analyze and assess 1 terabyte worth of data, but overall I have 3,000, maybe 10,000 terabytes worth of data. Now, what would you pick for analysis, right? Because if this is giving you 90% of insight of the entire thing, don't you think it's economical, it's efficient, it's faster, sometimes it's even better, right? That's exactly why we need this. So the next question you'll have to be asking at the moment right now is, okay, so we know what sampling is. Sampling is basically picking up 1 or 2 things out of the entire thing. It can be just 1, it can be 2. If you have 10 items in your population, even if you pick 9 out of 10, that is still called as a sample space because it does not have everything at the end of the day. So how do you go about picking up a sample? One very interesting thing is there's 2 ways of how you can do it. One is called random sampling and the other concept is called as clustering. So let me tell you what random sampling is, right? So if I basically give you a box full of Lego bricks, various colors of Lego bricks, I mix it up to you and I give it to you and you say, hey, you can pick up anything you want. What would you probably do? You just put your hand in it, pick up some Lego Jenga blocks, whatever it is, and you put it on the ground. So you randomly picked it, right? You're not searching inside that. You're not picking it one by one. You just picked up everything, put it on the ground. Maybe like how kids do it, right? So that's random sampling. We have something called clustering. Clustering is when you you have a data set full of similar and dissimilar items. What you do is whatever is similar, you make tiny groups out of them and you eventually work on all of those as individual groups themselves. Again, one more example. This time in a basket, I'm going to give you apples, oranges and bananas. I'm going to give you 3 fruit. I'm going to jumble it all up and I'm going to keep it in front of you. And I'm going to say, hey, can you keep all the bananas to the left side? Keep all the oranges in front of you. Keep all the apples to your right side. Can't you do it? If you can do it, yes, you've basically understood clustering to a good amount of moment, right? So basically we are determining by fruit. We are understanding what fruit has the same properties and we're just creating a small group out of them. So the next time I say, hey, for my analysis, I'm not going to require all the data. I'm just going to require a couple of bananas to test out a theory or a couple of apples to test out a theory. You have that cluster ready to go. You don't have to search for one apple in like probably millions of fruits out there, right? That is the advantage of sampling. That is the advantage of clustering. And either ways, now you might be saying, hey, isn't clustering such a nice approach? Why do we even require random sampling if clustering works really well? There are cases where randomness is preferred over having some structure to your data. Many cases where you're hunting for true randomness. Randomness in a computer is never true. Let me tell you this. You might write all the programs in the world to basically give you something random. 1, 2, 3, 4, 5 is what you would enter to your computer, and it can give you like a lot of combinations of random digits, ordering of that. But to randomize your own data, it will still be using certain formulas. It will still be using some vague logic out there. And if you can figure out those vague logic, you can backtrack your way and you can say that your data is not so random as you initially thought. And when that happens, we have a problem called as random biasing, and this just adds on and adds on, right? So there are cases where clustering works beautifully. There are other cases where random sampling is also preferred. This is very important for all of you all to know. So I hope you're clear with that. We can quickly go ahead and take a look at the next important part of our discussion, which is basically types of statistical analysis. Now, ladies and gentlemen, there are many ways of how we can go about performing any sort of analysis, right? You perform a lot of analysis in your head every single day. What's my day going to be like? How many hours of productive work I can go about doing today? If you're into running or something, how many kilometers I can run? So you're analyzing everything in your head. But when we put it all down to paper, there's 2 important types of statistical analysis out there. 2 very popular ways to perform analysis, in fact, that is qualitative analysis and quantitative analysis. Ladies and gentlemen, if you look at these individual terms to a good amount of detail, you will basically know what I'm meaning, right? Qualitative does not talk about quantity, but quantitative talks about quantity, right? Qualitative talks about the quality of the product. Quantitative talks about the quantity of the product, right? Now, to basically give you a picture of it. Now, if I give you a couple of pens and a couple of pencils, and again jumbled in a box, and if I say, hey, can you count how many pencils and how many pens I've given you? That's quantity. You're counting, right? You're performing analysis on a number, on a metric. That becomes quantitative because you have a quantity to think about. 3 apples, 4 bananas, 5 oranges. Think about it, right? And then we have something else called as qualitative analysis. Qualitative analysis is very simple. I'll give you an example. I'll say, hey guys, I'm going to give you a couple of pens. Each of these pens write in a different color. One is a green colored pen, one is a blue colored pen. The other one maybe writes in a shade of blue, writes in a shade of black. All these color pens, right? Now, color is not a number. Of course, your computer understands colors as numbers at the end of the day, but right now it's not a number. I've given you a couple of pens and I say, hey, can you actually go about keeping all the blue colored pens in one side, all the black colored pens in one side? You're basically performing an analysis, and what's your main point to actually go on to analyze? It's the color. It's not a number, it's a color, right? That's what makes it, that's what gives it a very important property of qualitativeness. Now, in fact, in this qualitative and quantitative divisions, that's basically for you guys to understand that we can also track a numerical metric and maybe a non-numerical metric as well. But in today's world, the way we actually perform statistics on paper is in 2 ways. It's inferential statistics and it's descriptive statistics. Inferential statistics is what you guys are after, and I definitely know that, right? So what are we talking about? We're going to be discussing this in detail in the next section as well, but let me quickly give you an introduction to tell you the difference between inferential statistics and descriptive statistics, right? Now, we already know for a fact that we usually take a certain sample space and not the entire population to make any sort of inferences. Again, the name inferential statistics, we are trying to infer something. We are trying to get an answer to a question that we are asking, right? So usually generalization is done in most of these cases to help you understand inferential statistics. Here's a very good example. I'll tell you, hey guys, here's a parking lot. There are 18 sedans, 4 SUVs and 3 convertible cars. Of course, all of these are cars, right? Now, all these cars are parked in front of you. Now I'm going to ask you a question and your answer is going to be an inferential statistics answer. The question I'm going to ask is, hey guys, which type of car is the highest numbered car that's present in our lot? Of course, you can see that there's only 3 convertible cars. There's only 4 SUVs, but there are 18 sedans out there, right? So when I ask you that question, which is the highest number of cars based on its type? The answer you're going to say is, hey, of course, there are 18 sedans and that's what it is, right? So you're calling an inference. You're basically making an inference, looking at your data, give me an analysis, giving me an answer to the question I just asked. This is a very good example of inferential statistics, right? Now, once we're done with inferential statistics, you have to also understand that, whenever you're performing inference, whenever you're inferencing on something, it's not really as easy as it sounds. And that's where another division into it called as hypothesis testing comes. Again, we have a section for this where we'll be discussing this, but to quickly give you a picture of what hypothesis testing is, hypothesis testing at the end of the day is basically us trying to see if certain conditions will be true for the entire population, right? What we usually do, we take a certain small sample set, we perform some analysis on it, and we assume that to the majority of the data set or the entire population it might work. But here we will be certain, we are for sure to say that, hey, this will work or this will not work, right? There's an example. Let me explain this in a simple way for you guys, right? Let's just say there are 8 people who came to attend a job interview. Now, out of these 8 people, let's just consider for a fact of only 1 person that is getting picked for the next couple of rounds, right? Now, what is the probability of this person getting picked? Of course, it's 1 divided by 8 because we are only considering 1 out of 8 people. So that person has a probability of 0.125. Correct? Now, if I say, hey, what is the probability that that person who we thought was picked was not picked? What is the probability of the same person not getting picked? So we know probability exists between 0 and 1. So all we have to do is we say 1 minus the probability of that person getting picked will give us the probability of that person what? Not getting picked, right? So the probability of the person not getting picked is 0.875. So there's a very high chance that the person is not getting picked. But what if the person gets picked for the first round, but eventually doesn't make it to the second round, right? So when a person makes it to the first round and doesn't make it to the second round, we have to consider the case of this person not getting picked later on, right? Getting picked once, not getting picked later. So it's basically 7 by 8. 1 minus 1 by 8 is nothing but 7 by 8. So we take 7 by 8 and multiply it 2 times, and we get to understand that this is the this is the probability of the person not going through the second round, considering he or she makes it through the first round. It's 0.765. So when you start to understand things in such a way, this is what hypothesis testing is all about. We consider that one of the results and one of the assumptions that we have made might be the same. In fact, that's the concept of null hypothesis and alternate hypothesis. We're going to be discussing this in the next section. But we assume certain things and we try to derive certain results. And once our assumptions and results come out to be the same, we can be like, hey, whatever hypothesis I had in mind was correct. It's basically us trying to make a very calculated guess, and we're trying to answer if your guess is correct or not, right? Two important things you have to consider in the case of hypothesis testing is, you might, as I already told you previously, right, you might think your data is random, but at the end of the day, if you find a way to make your data not random anymore, if you find a way to reverse engineer and come to your data and eventually say, hey, I had a formula and I just threw the formula in and it gave me the data in this order, it doesn't become truly random then, right? So randomness and a concept called as biasing, where your data can shift to one or the other side, which might confuse everything done later from that point, is something you have to understand. And these are like super important things which will have an effect on inferential statistics, which will have an effect on hypothesis testing as well, right? Now that's inferential statistics. Now that you know a tiny bit about inferential statistics, let me quickly bring you to descriptive statistics. Descriptive, I'm not trying to infer anything here, I'm trying to describe something, right? Descriptive statistics talks about how you can describe the data at hand, how whenever you're asked a question, your answer is going to be descriptive towards the question that gets asked, right? Let's consider the exact same example. We have 18 sedans, 4 SUVs and 3 convertible cars. Now, if I say, hey, how many cars are there which are blue in color, or how many sports cars are out there, you can say that, hey, listen, there are 4 sedans that are blue in color and there are 5 cars in total which are basically a sports model. Well, now even though you gave me numbers, even though you said, hey, 4 sedans, 5 colors and all of that, but overall, what are we looking at? We're looking at if they are blue in color, if they are a sports model. We are trying to describe the entity in itself, right? That, to a certain extent, is a very good introduction to understanding what descriptive statistics is. Well, now we took a look at a lot of things. We understood statistics, we understood the type of data, we understood how we go about picking up the data, various ways to go about understanding randomness, clustering and all of that. We had a very quick introduction and a comparison to understand between, the inferential statistics, the world of inferential statistics and the world of descriptive statistics as well, right? So let's take a couple of minutes to have a deep dive into inferential statistics to actually understand more about this domain, right? Now, as I told you, whenever we use a concept, let's just say such as descriptive statistics, you have to understand that descriptive statistics is a domain that is describing the characteristics of the data. Now, you can use various metrics to go about doing it. The example I gave you basically spoke about colors and sports model and all of that. When you describe the data, you can in fact describe it on the lines of mean, the average. You can talk about the median, the middle element. You can talk about the mode, the one that is, common. So what you can basically do at the end of the day is you can use mean, median, mode, variance and all of these concepts to basically summarize your entire data, describe the data by making use of numbers, by making use of graphs and whatnot, right? This is you describing the data. Now coming to inferential statistics, it's slightly different here because we're not trying to guess, we're not trying to use mean, median, mode or anything to give us the result, but here we're trying to make an inference of it, right? We're trying to get some conclusion, we're trying to draw some conclusion from the sample and say, hey, if this is true for the sample, I can make an inference that it might be true also for the entire population that I have. You get the difference now between inferential and descriptive statistics, right? So to add a little bit more clarity for your understanding on this, consider a situation where we might have to find out the average salary of, let's just say, a data analyst, right? Now, how can you go about finding the average salary of a data analyst? There's two important ways of how you can do it, right? First option is basically to consider all the data of all the data analysts that we have in India. We go to each one of them, ask them, hey, what's your salary? And we find all the salaries of all the data analysts in India, take an average of it, and you have an average salary of all the data analysts in India. One option, not very meaningful, but one option. The second option is to basically say, hey, I don't want to go to all the individual data analysts out there. What I'm going to do is I'm going to go to the major IT cities in India. Think about Bangalore, think about Delhi, think about Bombay, and all these places. I'm going to go there. I'm going to find all the, I'm going to sample all the data analysts there. I'm going to take their salaries and eventually consider that as an average and use it as a stepping stone, use it as an inference that maybe, these salaries have the most effect and say. And I can also say that from these IT hubs worth of salaries, I can say that maybe in all of India this is what data analysts make. And in fact, that's how we are going about doing. So whenever you go to Google and say data analyst salary in India, it's not like one person went to all the data analysts to ask their salary, make a calculation. This is exactly what happens, right? Second option. So to know that you've already used inferential statistics and now to find out what this is and how this works, I'm sure you're having a fun moment learning this one, right? So the first option, as you can already think of at the moment, is actually not very plausible. We have over 1 billion people here in India. I don't think it would be wise to go about asking each one of them about their salaries, right? So it is very time consuming. It is costly. It doesn't happen. It doesn't make sense to a certain degree. So to overcome this problem, we look at the second type of it, where we take a small amount of salary data, find their average, and eventually use that to make an inference and say, hey, we collected a sample. We collected a high quality sample, right? I'm not just asking for, I'm not looking for these outliers, for example, right? You know, data analysts make a ton of money. So basically, I don't want to just pick up the extremely rich data analysts there because that's going to mess up all the data for everyone else. I'm going to find an average. I'm going to find a balance in the sample set itself, so that as soon as I look at the bigger picture, that the small thing is just going to expand out and not just go way out of proportion, right? That is something which you have to consider here. So at this moment of time, you know what inferential statistics is, you know how it works, you know a couple of examples, you know its importance, you know where it is used, but you might be asking a question saying, okay, so why is it so important? Why is inferential statistics so important in today's world? Well, let me tell you one thing about inferential statistics. Making conclusions from just a sample about an entire population is how the world is basically working right now. The data analyst example should give you one example out of millions and millions of examples that you can think about, right? To conclude about something, to say, hey, I have a small sample and I've analyzed this and I can statistically say that this is very much significant to what happens in your entire population. Not. Maybe it will take you, one entire year to find out the salary of each and every data analyst in India, but having a sample set and doing it maybe might take you 1 day. So 1 day versus one entire year of work, which would you prefer? And at the end of the day, your result is going to be very, very, very similar, very, very close, right? So to find out what is more better, what is more statistically significant is why we use inferential statistics a lot. And in the case of machine learning, where we use a concept called as feature selection, feature engineering, all of that, where we have to understand, hey, adding these columns or adding these amount of data will either improve your machine learning model or it's going to decrease its efficiency, right? Either it will help it understand something better or it's going to confuse the hell out of your machine learning algorithm, right? That is also something that you can figure out by making use of inferential statistics. Now, when we talk about inferential statistics, you also have to understand that in today's world, right, there are many, many ways, there are many, many concepts that we have that govern the world of inferential statistics. As you can see on your screen right now, 4 very important concepts: probability, conditional probability, the central limit theorem, or it's called as a CLT, very popularly, and hypothesis testing, right? So let's quickly jump right into each and every one of them and understand what they are. Firstly, we have probability. Probability in itself, I'm sure you might have studied this in college or school or anything as such. This is us trying to find out, we're trying to measure the chance of something occurring, right? Now, if I have a dice, the dice that we use for games, which has 6 faces, and if I say, hey, what is the probability that I throw the die and I get, I land a 1, I land a 2, I land a 3, right? It's basically 1 out of 6 because it's only one choice. When you when you throw a dice, it will not sit in between and you can do an average of those two. It doesn't happen. Think about a coin toss. A coin toss is either heads or tails. There's only two options and you have a 50-50 chance. It's either this or it's either that. How do you know you have a 50-50 chance? Because you have only two outcomes and you have to pick up one outcome out of that. So 1 by 2 is what? 0.5. 0.5 is what? 50%, right? That's the world of probability out there. Now, to give you a little bit of clarity about the terms that gets thrown around in the world of probability, first we have something called as random experiment. Random experiment is where, it's an experiment where all the possible outcomes are already known. If I am flipping a coin, I know that there's only two options, right? It's either tails or it's heads. Now, some of you all might say, hey, the coin can also land vertically and it can be unusable. It's neither tails nor heads. But let's be honest, right? That extremely rarely happens, so we consider it as an outlier case. Next, we have something called a sample space. Sample space, as you already know right now, is basically a set of all the possible outcomes that we are going to take. It's a collection or a small amount of all the possible outcomes that we can have for a random experiment. Now, think about this. We're not talking about the population. Population is basically everything we have to assess. Sample space is a small collection or a set of all the possible outcomes that we have to consider, right? And then we have an event. An event is nothing but a subset of a sample space, right? Let me tell you that you have to throw a die, right? Maybe you're playing Ludo or something like that. An event is basically you throwing a die and saying, hey, now I need 6 to win, so I'm going to throw a 6. That's the subset of the entire sample space, right? Overall population, you can throw 6 ways in a single die, but now you only picked up one way throw it and that becomes an event. An event of you throwing a die to get a 6. Easily inferential statistics you can perform on it, right? And then you have something called as random variable. Random variable is basically a value, a variable whose value is basically subjected to certain variance, certain variations, certain randomness, and hence it's called as a random variable, right? When you pick up a random variable is when you have to understand one important thing, is the fact that it might, again, at the end of the day, same randomness concept that we had in our discussion. This is something even though it's random at the moment, it can have a lot of variations into it, right? So when I say, hey, randomly throw a die, you can get anything between 1 and 6. You cannot guess. And even if you do, it's a guess at the end of the day. But I can tell you, hey, there's a 1 by 6 probability that you're going to get that. And of course, it's going to be equal probability because if you have a fair die, which is where you don't cheat, it works, right? So that is a random variable. Now coming on to the concept of conditional probability. We know what probability is. Probability of event occurring, right? Probability is basically this limit between 0 and 1 where each of that can be a percentage. Now if I tell you, hey guys, what's the chance of it raining tomorrow? You might say, yes, it'll rain tomorrow, or it'll say it'll not rain tomorrow. But if I tell you guys, okay, so how much do you think it might rain tomorrow? What's the probability that it might rain tomorrow? And now you're going to come back with a number. Now you're going to say, hey, there is a 60% chance. There's a 60% probability that it will rain tomorrow, right? That's probability. Now coming to conditional probability. Conditional probability is very similar to probability, but here we're considering a situation where what is the probability of an event occurring if another certain condition has already occurred. I'll give you an example. If I say, hey, what is the probability that it will rain day after tomorrow if it rains tomorrow? You see that, right? There's a condition there. It's not just me randomly saying and talking about day after tomorrow's rain. I'm asking you a question saying, what is the probability that it will rain day after tomorrow if it rains tomorrow, right? There's a condition. There's two probabilities that you'll have to work with. And as you can see on your screen, it's a very simple formula. Probability of one more event occurring over the other is basically you understanding the probability of both the events occurring divided by one of these probabilities of the actual later event that we have in the discussion, right? And as you can see, n of x basically gives us the total cases which are favorable to the event x. In our case, event x can be considered as maybe tomorrow's weather, and eventually x intersection y is basically telling us all the chances of tomorrow's rain, all the chances of day after tomorrow's rain, and eventually then we get to make a connection. This is how we usually go about writing the formula. P of x intersection y divided by p of x, basically probability of x. But as you can always tell, it is very important to mention this thing at the end to say P of X should be greater than 0. Probability can never be negative, but the probability can be 0. If it does not rain tomorrow at all, you can tell me, hey, there's a 0% chance of it raining tomorrow. But it has to be, in this case, we cannot divide something by 0, right? So there has to be a chance of something occurring. That's when we say P of X should be greater than 0. It can be 0.0001, but it has to be greater than 0 because we cannot divide anything by 0, right? That's conditional probability. Now, let's quickly take a look at the central limit theorem. Central limit theorem, or CLT. Don't worry, I'm not going to bore you with how we go about deriving a theorem and all of that. But what CLT or central limit theorem tells us is for a fact that whenever we go on to increase the sample size, the overall distribution of the sample, right, that becomes normally distributed. Now, when I say when you increase the sample or something, let's just say right now you have an entire bag, you have a truck, let's just say you have a truck full of fruits right now. You picked up a couple of fruits, you picked up 10 kilos worth of fruits. Now what I'm going to say is, hey, pick up another 25-30 kilos of fruits, right? Now you just picked up a lot of fruits. What's going to happen now with your data is, initially what you might have thought of how your data is divided, now it's going to follow something that's called as the normal distribution. Normal distribution is that bell-shaped beautiful curve that you might have studied about or you might have seen, right? So why the central limit theorem is even in discussion is for a fact that this theorem appears to be true. It is practically and particularly true for cases wherever we have a sample size which is greater than 30. So the overall conclusion is that if you have greater number of samples out there, particularly of large sizes, the distribution is, I'm not going to say it's 100% normal distribution, but what it's going to do is it's going to follow very, very, very closely to what the normal distribution curve looks like. So think about it. You would have never thought about it, right? You might have had a question saying how much population we should pick up and does it have an effect? The central limit theorem tells you how much population will have what sort of effect on your data, right? If you pick up a small amount of data, you can say that the distribution is maybe not normally distributed. But as you start growing and growing and growing your sample set, it will start following that, right? And that will give you a conclusion that will give you an understanding saying, even though I thought that picking up 1, 10 or 20 might not have any meaning, but now as soon as you start picking up more and more and more data from your sample set, from your overall population, you will get to know that it does have an effect, it does change something, and if that goes unaccounted, whatever you're doing later might have less accuracy or it might not be as efficient as you can think, right? This is very important for you to understand. Now let's come to the part where we were discussing hypothesis testing, right? I have a beautiful example to tell you guys what hypothesis testing is and how you can go about working with it. Now, as we already saw in the quick introduction we took previously, hypothesis testing is a very, very, very important part of statistics. And here we just make assumptions. We start out with assumptions and we try to see if our assumption was right. We try to see if your end result is exactly what you thought would be the result, right? I'll give an example. You know the planet Pluto, right? The concept is very simple. Starting people, thought that Pluto was a planet. And if you remember the news a couple of years back, they said, oh no, Pluto is not even big enough to be a planet, so it's no longer a planet, right? So they just basically removed the planet aspect of an entire planet out there, and Pluto, of course, right? Sad for Pluto. But later they said, oh no, we're going to be still considering Pluto as a planet because they had certain characteristics to it. So the process where we assume something first, and maybe we also have a case where the assumption is correct, where the assumption is wrong, that is how we play with the world of with the world of hypothesis testing, right? So two concepts, we have null hypothesis and alternate hypothesis. Null hypothesis is the observation that you would do which is completely by chance. Someone out there might have said, hey, I can see Pluto there. Pluto is also part of solar system, so let's consider Pluto to be a planet. That is a null hypothesis that can be considered as H0. Now, alternate hypothesis. What do you think of the alternate hypothesis is? Here, we are not assuming anything by chance, and these are some things that gets affected by non-random situation. An alternate hypothesis at this moment is me saying Pluto is not a planet. And of course, there are scientists who are going to come and say, hey, yes, Pluto is not a planet because these situations, these examples, these numbers, these metrics, we have a minimum size for a planet, for a celestial entity to be called as a planet. So it doesn't cover it, right? So what you just did was you assumed something and eventually you had proofs to either prove one of these conditions correct. And once you prove one of these is correct, the other one goes right right out the window, right? Because if I say null hypothesis that Pluto is a planet, and if I say alternate hypothesis Pluto is not a planet, as soon as one gets proved that it is absolutely correct, what happens to the other? It goes right out the window, right? So this is something which you should assess and analyze as well. Alternate hypothesis is usually denoted by H1 or HA or a couple of variables like that. But always understand, whenever you say null stands for zero. Easy way to remember is that H0 is nothing but the null hypothesis. H1 is nothing but the alternative hypothesis, right? So the question you should be asking is, how do you know whether you're supposed to reject your null hypothesis, or what happens when you fail to reject your null hypothesis and all of that, right? So we actually have 4 steps of how we can go on to determine this. The first step for us is to actually say what the null hypothesis is, say what the alternate hypothesis is. Once we go about understanding what each of the hypotheses are, then we'll have an analysis plan to find out how to use the sample data that we have to figure out if we can prove the null hypothesis correct. Later we go about doing certain tests there. We try to see if Pluto is a planet. Our assumption was Pluto is a planet. Now every one of the scientists is going to be working to prove Pluto is a planet, right? And then we have something called as a test statistic that we go about using here, and understanding what are the decisions that we took to claim that Pluto is either a planet or not will eventually have a final say to tell you if your null hypothesis is true or not. Now, on a very vague example, if I tell you Pluto should be of the size 10, but Pluto is actually size 9, but my initial null hypothesis said Pluto is a planet. Now you will figure out that your null hypothesis is wrong. Pluto is no longer a planet because it does not meet the minimum size that's required for a planet. Right? Look at that. We actually did 4 steps in just 2 sentences of what I said. Once you figure out, it's an easy way to go about doing it. Statistics is extremely easy. It's extremely fun to work with at the same time, right? So this is something really important for all of you all to understand. Now, that number, that metric we associate with a couple of tests that we do to say, hey, if we can accept the null hypothesis or not. It's basically a lot of tests that are out there, and we have something called as a significance level, right? Sometimes it so happens that I give you a very clear example. Sometimes it so happens that your null hypothesis is sort of over the edge. It is still confusing. It's not as clear as Pluto being a planet or not. You might think that maybe it is correct or maybe it's not correct, right? So we will set something called as a significance level, and we'll say, hey, we will reject the value of null hypothesis if I have a metric called as the T-stat metric or anything, which is eventually lower, right? If your significance value, if it is lower than your significance value, we will say we're going to be rejecting the null hypothesis, or we will say we accept the null hypothesis, right? Now, that's where the catch lies in. You can reject the null hypothesis, but you can say that you cannot accept the null hypothesis either way, right? Because you say either you fail to do it, you reject it, or you say you reject the null hypothesis. So remember one very important thing about hypothesis testing. You don't accept the null hypothesis, you either reject the null hypothesis, or you accept the alternative hypothesis, or you reject the alternative hypothesis, which will eventually mean your initial assumptions have been correct, right? So there's no true case for null hypothesis in many situations. Of course, there are cases where you basically calling it on a verbal way means the same thing, but since you guys it's very important for you guys to understand these nitty-gritty tiny details which add so much value for your learning, right? So this is very important for all of you all to understand. Now, the important terms that we have in the domain of hypothesis testing, first of all, was significance level. What do we mean by significance level that I told you just about? Significance level is basically the probability of when we can reject the null hypothesis, but what happens if it's actually true, right? Look at the example on your screen. It says a 0.05 significance level indicates that there is a 5% risk in assuming that there is difference when there's actually no difference at all. Now, when I ask you guys saying, hey, the air in your tire seems to be low on your car or on your bike, and there seems to be a 5% risk that there's a puncture, right? Now, in real, there might have been never a risk, but I said, hey, there's a 5% risk, right? Now, I added significance to something which did not exist. I added significance to a case. I added significance to an assumption that your tire might be punctured. You getting that? Where we set the significance. Now, I'll say, hey, it's this 5% that we think it's punctured, right? Maybe it's fine. Now, if that number was, hey, I think there's an 80% chance that your tire is punctured. what would you do then? Would you still write it? I don't think so, right? So this significance level is basically denoted by alpha. So whenever you go about seeing these terms like alpha and all of that on hypothesis testing, do not be confused. It's basically a significance level telling us basically if the probability of a case where we reject the null hypothesis can be false, but in actual case it might be true as well, right? So this is something which is important. The other term that you might see a lot is basically the p-value test. P-value is basically defined as us seeing the t statistic that we spoke about as an extreme calculated value, but this case only happens if your null hypothesis is true, right? So at the end of the day, for you to understand about p-value, you have to understand that if your p-value is very low enough, that will give you grounds for rejecting the null hypothesis. If your p-value is low, you can say, hey, I reject the null hypothesis. And when you reject the null hypothesis, this only happens when your p-value is what? It's not just that your p-value exists, but your p-value is less than the significance level. Significance level is something we just spoke about, and there we spoke about p-value. You might have been confused what p-value is. So now we go on to discuss p-value, and you've understood significance level as well. So quickly, next we have another very important way in the world of inferential statistics. It's called chi-square test, or it's called chi-square test. Now there's various ways of how you can go on to pronounce this, say this. I love to call this as chi-square or chi-square, right? Now basically this test is us trying to say, hey, all these cases that we spoke right now was numerical data, right? If Pluto was size 10, if Pluto was size 9, something like that. But what do you do with categorical data? What do you do with textual data when you have to perform some inferences on that, right? This is where the chi-square test comes into the picture. When you have to compare two categorical data entities, this is when you would use something called as the chi-square statistics. And basically there's two types of chi-square. We have the chi-square statistics and the chi-square distribution, which again are used for very, very different purposes. Now don't worry, I'm not going to go very much in depth because this can definitely confuse you guys if you are beginners. But there are two things you have to understand regardless. It's goodness of fit and it's test of independence, right? So let's talk about goodness of fit for a second. Goodness of fit is basically us trying to figure out if the sample data that we have, the categorical data that we have, will it match the entire population that you have, right? Now, you remember, we take an entire population, we consider a small sample set out of it. But if you have a data point and you want to see if data point fits into an entire, an entire population, it's the reverse process. Here you have to see if it fits correct or not. If I give you 10 apples and if I say, hey, there's a truck full of oranges, just throw your apples into those oranges, it doesn't make sense, right? So this is when we figure things out. We see if it is a good fit or not, right? That's goodness of fit. And then we have something called as test of independence. Test of independence is where we basically go on to compare two categorical variables and we try to see if if they are related in some way or another. Now, Pluto can very much be related to Earth because Pluto is round, Pluto is a planet, Pluto is also revolving around the sun, Pluto is maybe spinning just like the Earth as well. Pluto it's extremely far away from the sun, but maybe it sees the sun as a tiny little dot, but it does see the sun. We also see the sun, it goes around the sun, we also go around. You're seeing this, right? There is certain interdependence there. It's not like it's completely independent in that case. So whenever we have two categorical data elements and we want to see, hey, if these two elements are related to each other in any one way, right? It can definitely, one thing can definitely lead to the other, right? If two things are related, it does happen. If two things are not related, also it happens, but that's a different case. So guys, this is some very important things you have to know about the chi-square test. Right? Fantastic. The next thing we have is basically ANOVA. ANOVA basically stands for analysis of variance. Now, whenever you're working with the concept of inferential statistics, how do you figure out if your experiment results are either significant, they're accurate, or they're not significant, right? So basically we have ANOVA, analysis of variance. What we do is, we use this wherever we have cases where there are more than two groups and we have to test the hypothesis, right? We have to test that, hey, consider the mean of multiple population, consider the variance of multiple populations, and they are to be equal as well. I know that might sound a little confusing, so let me add a bit of clarity by giving you an example. Think about the example, right? Students from different colleges. You have one university. You have one university that governs all the other colleges out there. So students from various universities take the exact same examination, and what we will try to see at the end of the day is if your college performs better than another college that's out there. Right now, you're taking an entire population, you're taking a sample set, you're figuring out the results of your college, you're figuring out the results of some other college, and you're figuring out probably results of 10 different colleges to see who did the best when you were given the same thing to work on. How much of a variance do you see from the same data point is exactly what ANOVA talks about. And in fact, there's two ways of how you can go about with the ANOVA test. It's the one-way ANOVA and we have the two-way ANOVA, right? Now, going into the depth of one-way ANOVA and two-way ANOVA can definitely add more to your confusion, but you have to understand this moment of time, everything we have discussed, right? Probability, conditional probability, ANOVA, all these statistical testing methodologies, hypothesis testing. This is very important to add as a foundation for all of your learning. So with that, we have come to the end of this course. Thank you so much for watching. To summarize everything that we have learned on this course, we started this one out right at the basics, right at the foundations. We started out by answering a question: what is statistics? How is it valid for us in today's world? We took the data science example. We understood how it works. We understood what are the various types of statistical analysis we can go on to do. What are the various types of data we can handle? And in that data, we had more data. And in that, we had multiple types, right? So we took a look at a lot of types of data. We took a look at a variety of ways of handling these data, how we can go about to sample the data, how do we collect data for statistics, how does statistics work, and eventually we dive right into understanding a little bit about descriptive statistics and a lot about inferential statistics, right? So that introduction section would have given you a small direct comparison between descriptive statistics and inferential statistics, and then we took a deep dive into inferential statistics and we understood all the various methods of how you can go about working with inferential statistics, and we discussed some very important pillars of inferential statistics such as probability, conditional probability, hypothesis testing, ANOVA, chi-square, chi-square test, right? And you can say it any other way, right? So basically we understood a lot of things. So guys, with this course, I hope all of you all are cleared with all of the concepts that we covered in today's course, right? On that note, again, thank you so much for watching. My name is Anirudh Rao and I'll see you on the next one.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleague, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.